I'm going to talk about a light scalar field in this theta. We want to consider the following setup. We have an observer in this theta. This is the region which is causally connected to this observer. The metric of this patch of the theta, if we set the curvature scale to 1, is given by this equation. This is time independent, and hence the patch is called the static patch of the theta. We want to consider the scalar field, a light scalar field, and ask if the observer measures the correlation functions of phi, how would they relax in time? Let us first consider a free scalar field with a small mass. In this case, the standard approach to this kind of questions is to calculate the quasi-normal modes. These are the eigenmodes of the Hamiltonian with the right asymptotic behavior. In our case, it is outgoing boundary condition at the future horizon and regularity at the origin. The frequencies of the quasi-normal modes are discrete, and in this case, the lowest lying mode, which is an L equal to 0 mode, has the frequency that is given here, which is a result that is well known to cosmologists. Now we want to ask a similar question, but in the presence of more general interactions in the potential, not just the master. So for instance, we can consider lambda phi to the fourth theory, with lambda much smaller than 1. This problem is non-trivial. We cannot treat the interaction perturbatively. Let's assume the converse. If we try to estimate the variance of the field and assume that it is dominated by the mass term, then the variance would be of order 1 over m squared. If we compare the lambda phi to the fourth interaction with the mass term, then we get lambda over m to the fourth. Since m is measured in curvature units, it is much less than 1. Therefore, this ratio can be very large. For instance, if we take mass to be something which is technically natural, so if m squared is of order of lambda, then this ratio would be of order 1 over lambda, which is very large for a small lambda. This problem of the breakdown of perturbation theory in the theta is a well-known problem, and it was studied about 30 years ago by Stravinsky and by many others since then. In the standard approach, one usually studies the problem in the expanding patch of the theta, which is shown on the left. The goal here is to study the same problem but in the static patch and try to formulate a perturbative expansion for calculating the relaxation exponents in the presence of the interactions. Let me mention that the analog of Stravinsky is a smeared field, which is the field smeared over some superhorizon region with a fixed physical size. The analog of that in the static patch has a very natural interpretation as the object that is accessible to an individual observer. Even though gravity is non-dynamical for us, or we assume that it is non-dynamical, in case we want to consider dynamical gravity, the setup on the right seems to be a more well-defined setup to consider. Okay, so with this introduction, we want to calculate the correlation functions in the static patch. In order to do that, we need to know what the state is. So we are considering the Hartle-Hawking state for the field in the theta. The Hartle-Hawking state is obtained by taking tau to eta, where tau is the global time of the seeker. So after this big rotation, the metric of global de Sitter becomes the sphere metric, and the Hartle-Hawking wave function for a given configuration of the field is given by doing the sphere path integral, the path integral over the Euclidean de Sitter, which is or half of the Euclidean de Sitter, which is the hemisphere, with the boundary condition imposed at tau equal to 0. The wave function for later times is obtained by evolving this wave function with the global time Hamiltonian. However, we are interested in the state in the static patch. The static patch contains only half of the tau equal to 0 state. So the state in the static patch would be a mixed state obtained by tracing over the left side. More explicitly, the density matrix in the static patch is given by the path integral over cut for a sphere, where on the two sides of the cut we are imposing boundary conditions which correspond to the two arguments of the density matrix. The Hamiltonian in the static patch, the generator of the time translation, which is an isometry of the Sitter, it becomes the generator of the rotations around the horizon, which is the center in this picture. So if we slice this path integral in that direction, we see that the Hartle-Hawking state is a thermal state for the static patch Hamiltonian with temperature 2 pi. Sorry, with temperature 1 over 2 pi. Now, given the state at some time, say at t equal to 0, we can find rho of t by conjugating it with e to the minus iht. In the Hartle-Hawking case, it is an equilibrium state, so it doesn't change in time. In this state, we want to calculate the correlation functions in time of some simple observables, which, for instance, we consider to be the field smeared in the vicinity of the origin. Instead of this object, we can instead consider perturbing the state by inserting some operator, and then study the evolution of the reduced density matrix for this simple observable phi bar. So we want to calculate dt of rho. If we take the size of the smearing region to be sufficiently large, or average quantities over some time interval, then the off-diagonal elements of this density matrix become small. And we can focus on the diagonal element which have the interesting physics. So let us ask, what is the Hartle-Hawking state for this diagonal element? In order to calculate it, we should glue back most of the degrees of freedom on the two sides of the cut that define the density matrix in the static patch. The only thing that is left fixed is the average field phi bar, which has been set to phi on both sides because we are looking at the diagonal component. If V was constant, then the solution, the saddle point of this Euclidean path integral would be just phi equals a constant, curly phi. If V is not constant, but it is slowly varying, we still have a saddle which is close to that, with corrections which are controlled by the derivatives of the potential. So we get this famous result for the leading equilibrium distribution. What it tells us is that even though if we had a field with V equal to 0, which has a shift symmetry, it would diffuse. After we consider potential, no matter how shallow it is, this diffusion is going to be contained, and we get a distribution which is peak near the bottom of the potential. However, if the potential is shallow, the variance of this distribution is going to be very large. In this same setup, we could also ask about the Euclidean correlation functions. And in principle, we could understand the answer to our question, the relaxation exponents, by calculating these Euclidean correlation functions and analytically continuing to real time, to Lorentzian time. However, to understand the behavior at very late time requires calculating this object with increasingly large precision. And that doesn't seem to be easy for generic interactions. Instead, we take a real-time approach and we try to calculate the evolution of the perturbed distribution after long times. So the way we define it is that we insert some projection operator at some early time. Here we insert it symmetrically along the thermal circle, and then evolve the density matrix forward in time. So the object that we want to calculate or we are interested in is something that is defined by the path integral like this. In order to be able to calculate path integrals like this, we need to understand we want to calculate these path integrals perturbatively, or at least find some way of approaching it using perturbation theory. So we should understand the mode expansion of the field. The free action, which we consider to be just a kinetic term, if we write it in the tortoise coordinate x and we expand the field in terms of a spherical harmonics, is given by this expression. Here, the effective potential has been plotted. I have also included the master. And what we see is that this effective potential, they decay as x goes to infinity, which is the location of the horizon. Even if we had the general potential, it would have the similar behavior. They would decay as x goes to infinity. So what it means is that we have a continuous spectrum in this model. And in the case of L equal to 0 modes, that continuum extends all the way to the origin, x equal to 0. It is the infrared modes that lead to the non-trivial late time behavior. The infrared modes that extend all the way to 0, meaning the L equal to 0 infrared modes. They contribute equally to the observable of interest. These modes are highly excited at the zeta temperature, and therefore they lead to a divergent variance in the thermal state. Or if we consider the projected state into that boundary phi b, then we get diffusion. So now we want to consider including interaction in non-zero v of phi. So as I mentioned before, this interaction is local as near the origin. But this is the blue curve here for the mass, but also for generic potential. It would be local as near the origin with the characteristic size 1. And that means that it introduces an all-to-all coupling for this infrared L equal to 0 modes. If we consider the simple example of m squared phi squared, then we can diagonalize the full Hamiltonian. And what this additional potential does is that it suppresses the low frequency modes near the origin. And that's how it changes the late time behavior. But for general V, For general potential, we cannot diagonalize the full Hamiltonian, so we want to find a perturbative approach. However, this perturbation theory cannot be just a perturbation in V, because the distribution that we have, it should start from something that diffuses, but at late times it should go to this equilibrium distribution, in which the potential is dominating. So we cannot just perturb in V. In fact, we have to treat the infrared modes non-perturbatively. What can be calculated perturbatively is the time derivatives of P. And this is given by the famous result that was obtained by Starbinsky, is given by this Fokker-Planck equation at leading order. This equation has a remarkable property that, it is independent of the history. It has no explicit T or phi B dependence, or in other words, it is Markovian. Given this equation, we can start from the state of the system at some moment and then integrate it forward for arbitrarily long time. And we can obtain the relaxation exponents and the equilibrium distribution. An alternative way of describing the Markovian evolution is to say that the time derivative of the correlation functions of phi at some time t, they only depend on the correlation functions of phi at the same time and not the earlier times. And this function f is what we can calculate perturbatively. So let us think about the underlying reason for this Markovianity. So let's see what we have done. What we have done is that we have integrated out all but one linear combination of the infrared degrees of freedom, which is this phi bar. We have integrated out all of them. And generically, in a normal situation, if we did something like that, we would get an evolution with a very long memory. But so what is the intuition behind the Markovian evolution in our case? If we go back to the cosmological analysis in the expanding patch of the Seater, then the reasons are one, the decoupling of the superhorizon patches and the classical evolution. And the other reason is the short memory of the short modes that contribute to the noise. These intuitions have become concrete in the work of Gorbenko and Senatore by working with the wave function of the universe. The counterparts of those intuitions in the static patch are the localization of the interaction near the origin and the finite temperature. These ensure that phi bar is the only relevant infrared degree of freedom, or it contains all of the relevant infrared degrees of freedom in the calculation of the time derivative of correlation functions, or the distribution. So let us consider this calculation. I focus on the calculation of the time derivative of the equal time correlation function. So our operator is made of one phi dot and a bunch of phi's summed over all possible permutations. This can be done using this is an in calculation. We can do it in the interaction picture. There is an initial state rho naught here. This initial state, for simplicity, we consider it to be a Gaussian state. It should be approximately thermal, but it should have a finite variance, which is something that we would obtain by this projection of phi bar into some boundary value. Beta here is the inverse temperature, which is 2 pi. Now, if we wanted to consider more generalistic, then we could add sources to the interaction Hamiltonian. These sources should have the property that they turn on after t equal to 0, but they should turn off well before getting to the time that we are calculating the correlation functions. Now, what underlies, what allows us to formulate the perturbative expansion is a property of the contractions that we have in this in calculation. So, with our choice of a Gaussian initial state, we can expand this nested commutators in terms of the commutators and anti-commutators of phi I and phi I dot. And what we can realize is that there is a universality when we take one of these contractions and take them at a long time separation. So what happens is that the contractions of phi and phi dot go to 0, and the contractions of phi with itself, they approach the same result as if we consider just phi bar. So the differences here and these contractions between phi and phi dot, these are the objects that are dominated by order 1 frequencies. These objects, we call them short range links. And these are suppressed compared to usual contractions of phi. They're suppressed by 1 over the relaxation time, which is a long time. Because the contractions of phi are dominated by the infrared modes, while the contractions in these short range links, they are dominated by the order 1 frequencies. So the nature of the perturbative expansion that we formulate is an expansion in the number of these links, but we keep all orders of V. As usual, we can focus on the connected diagrams if we are only interested in finding the evolution equation rather than the actual answer. The connected diagrams in this context would be the set of links that form a chain that connects to the final insertion of phi dot. So here the final insertions are drawn by stars, and the phi dot is red while phi of t is black, and then black dots are the interaction vertices. There can be many other interaction vertices which are not contracted via the short range links, and the role that they play is to simply promote all interaction picture fields into the Heisenberg picture fields. So we call them just, we call them as dressing of the results that we obtain from this calculation. So let's see how it works in practice. We first consider just one link, the first order. And here we can look at two objects, first dt of phi bar squared, which is made of the anti-commutator of phi and phi dot. This is just one link, and it's given by 1 over 4 pi squared. And then if we look at dt of phi, then we can get the first order contribution by considering contraction between one interaction Hamiltonian and the final phi dot, and the result would be -1 star v prime. So here I indicated that this is a bare quantity because we only consider one interaction Hamiltonian. Once we include the include all higher order contributions in HI, what they do is that they make this phi I into just phi bar. Now, if we use the standard relation between time derivative of correlation functions and the time derivative of the distribution, we can easily translate these two results in the leading, into the leading stochastic equation for P. Now we can go to the second order. A second order for the dt of phi, we have two links, so we can consider these two diagrams, one including two interaction vertices, and one of them contains one with a loop. And then for the time derivative of phi squared, there is this one diagram. This diagram contributes a correction to the so-called diffusion term, which is proportional to V double prime. And then these two terms give these two corrections with alphas given here. Here, this curly L is related to the size of the window function, or a smearing function that we consider. Using this result, we can go ahead and calculate the relaxation exponents in a given theory. Say if we consider lambda phi to the fourth, we can calculate the first correction to the relaxation, to the leading relaxation exponents. So as I mentioned, the expansion here is in inverse powers of the relaxation time. The inverse of the relaxation time is determined by this same exponent, so this proportional to the square root of lambda. And as you see, the next term in the expansion is done by the square root of lambda. And another notable point is that, of course, as it should, there is no dependence there's no dependence on this L, the smearing length in the final result, because these relaxation exponents, they are late time or long distance observables of the model, so they shouldn't depend on the details of the smearing function. So to conclude, we argue that the evolution of the smeared field in the static patch of de Sitter follows the same stochastic equation that Stravinsky calculated, but we can also calculate the corrections perturbatively to this equation, and we included the first one. This is natural. This coincidence should be expected because the eigenvalues of the equation are long-term observables, and they shouldn't depend on the details of the experimental setup. One can think of these exponents as poser and S matrix-like object in the static patch because we can define the in and out state nicely in the static patch, given that the interactions, they all vanish as we go close to the horizon. And finally, the Markovianity of the evolution was made manifest by setting up a perturbative expansion in terms of the short range links. These are the contributions which are dominated by order 1 frequencies, while the infrared modes in this treatment were considered and taken into account non-perturbatively. Thank you.